Today's video lesson is dealing with the kinetic formula in a first-order reaction. What I have in front of me is my equation page that was handed to you the day we got our note pack out. What I'm examining from our formula page is the first-order reaction in which A is converted to B. We understand from the past few lessons about what's known as the differential rate law, staring down those data tables of initial rates and generating how the rate and concentration are related. In a first-order rate law, rate is equal to K times the concentration of our A raised to the first power. And since A is a reactant, we also express what's known as a rate expression, where the change in concentration of A over the change in time is known as the rate expression. Recall that as time goes by, the concentration is disappearing for the concentration of A, our reactant. In the new lesson presented today, we are going to take the differential rate law and turn it into what's known as an integrated rate law. Through the help of calculus, we are turning our curve into a straight line that has a y equal mx plus b format. By changing the concentration on the y-axis and the time on the x-axis into a straight line function, we are now able to relate the concentration of the reactant at any point in time in our experiment. Recall that in a differential rate law, we always begin with instantaneous rates. We're assuming that no product has formed. By integrating the rate law, and again, the math understanding isn't important, but to understand that by taking the curve and creating a y equal mx plus b format, the natural log of the concentration of our reactant A at any point in time in the reaction can be found by taking negative K, that's the rate law constant, times the amount of time that went by, plus the natural log of the original concentration of A. If we were to graph, y on the x-axis is the natural log of A. That's equal to negative K, where negative K is the slope of the line. This rate constant is the slope of this line. Since it's in a negative format, you see the negative in front of it. The x, of course, is the x-axis represented by time, usually in a second. And then, of course, the intercept here would be the natural log of A at time 0. This is where we're heading in the new lesson, is taking smaller steps to look at how a differential rate law can be used when integrated to calculate the amount of reactant left in solution at any point in time during the course of a reaction. I'm going to keep my kinetics formula page close by. We'll be referring to it again, but I'm going to ask that you find your note packs and we'll follow along. We're on page 6 where it's reading about the concentration with time. Friends, this is also available on the website in a PowerPoint format. The PowerPoint is on a different link. If you'd like to look at that as well, feel free to do so. I'm going to choose to just look at the note pack, what we have in front of us. We are studying section 4, the change of concentration with the change in time. We are looking to take our differential rate law and integrate it, what we discussed a moment ago. In our first bullet under this section, it reads, rate laws enable us to calculate the rate. Let's go ahead and fill in the rate from the rate constant and reactant concentrations. Rate laws, just as in the example up above, rate is equal to K times the concentration of each reactant raised to some power. We are going to take a look at how the constant and the concentration can be used to calculate rate. Rate laws can be converted into equations that tell us the concentrations of the reactant or product in any point in time during the course of the reaction. To understand the calculus will be Mrs. Milder's job. We will share with you the formulas to go from a differential to an integrated rate law, taking a curve and turning it into a straight line formula. Now, in a differential first-order rate law, it describes exactly how the rate depends upon the concentration of each reactant. Differential rate laws of what we've been practicing. Rate is equal to K times the concentration of the reactant raised to some order. We are seeing today that an integrated rate law describes how the concentration out of a reactant at any point in time can be calculated. So we're looking at how all the differential rate laws, there is an integrated rate law and vice versa. For every addition problem, there is a subtraction problem. For every differential rate law, there is an integrated rate law. Remembering that rate laws help us understand in our last sections how reaction mechanisms work as well. Rate laws give us great insight into the number of collisions necessary to produce a desired product. So remember, differential rate laws show us the relationship, such as rate is equal to the concentration of our reactant A changing over time, and we've expressed that as rate is equal to K times the concentration of A raised to some order. Could be first order, second order, our most common ones that we're solving. Differential rate laws, in the next bullet says, shows how rate depends on concentration of reactants. I stare down data tables looking at rate and how it's influenced by manipulating each reactant, holding others constant. The concentration of the products do not appear in the rate law because it is an initial or instantaneous rate. Remember, at time 0, there are no products. They haven't been made yet. We also remember from our previous lessons that rate laws have nothing to do with stoichiometry, but must be determined experimentally. They can't be obtained from the equation, but they must be derived by looking at data. Moving from what we know already and have practiced, differential, to the new lesson today, integrated rate laws. It reads, if we integrate this equation, this relationship can be transformed into an equation that's related to the concentration of A at the start of the reaction to the initial concentration at time 0. And that is going to give us another time called T. Any other time that's gone by, we can calculate the remaining amount. For those of you who are familiar with calculus, that relationship would be set up. Concentration of A at any point in time and compared to time 0. You might have seen this in Mrs. Milder's calculus class, but this is all we're doing. We set that familiar equation to integrate, and what we're able to do then is to compare the remaining amount of reactant A over a course of time, knowing reactants get used along the way as products get made. Again, this part, not important, but just showing those who are interested. We'll move to our second page on this particular lesson. When we begin looking at concentrations as a function of time, we refer to those as an integrated rate law. So let's fill that blank in. The concentrations as a function of time. And what that's allowing us to consider, not only can we figure out the initial amount of our reactant, we can figure out how much reactant is left over a course of time simply by knowing the rate constant K, which is the slope of our line. So it forms an equation